room up in the front for the A students if you want to come up here. All right. Well, today we'll be pleased to hear from Dr. Michael A. Sutton. Dr. Sutton received his PhD from the University of Illinois and then joined the faculty in the Department of Mechanical Engineering at the University of South Carolina. He's currently a research professor and director of the State Center for Mechanics, Materials, and Non-Destructive Evaluation, while serving as the Chief Science Officer for Correlated Solutions. As one of the inventors of digital image correlation methods, he's co-authored the only book on image correlation methods. Dr. Sutton, we look forward to hearing from you.
Thank you. It's a pleasure to be here. I'll get started on the talk. It runs around 45 to 50 minutes, so we should be in good shape. As you can see, the talk is set up here. We'll have three parts. I'll spend the first 15 to 20 minutes talking about the basics in digital image correlation for image matching that forms the foundation of the technology. A lot of people know this already. For you, it'll be a review. For those that don't know much about it, I'll do my best to try to explain the fundamentals in a very brief manner. In the second part of the talk, we'll be using the image correlation method with a series of experiments done at the Ohio State University with a good friend of mine, XLIII, on a Hopkinson bar. I was particularly interested in the very early stages of mechanical loading as the wave propagates in. When it's in dynamic equilibrium, the accelerations have not decreased. They're relatively high, yet the stresses still are to be determined because it's no longer in a quasi-equilibrium state. So that was the focus of this work, and we'll talk a good bit about that. The last part will be the recent developments on modal analysis with image correlation. It's been around a while, but more in the last 2 or 3 years, it's expanded greatly the capabilities. So I'll spend the last 10 or 15 minutes on that, which is primarily the focus of the conference. I need to start out by thanking Tyler and the IMAC community for inviting me. It's been a long time since I've been here. The last time, I'm a solid mechanician primarily, so I spent a lot of time in SEM and ASME. Last time I was here was in 2002. Many of you may remember, those that were here, that wasn't a good time. It was right after 9/11. There wasn't a lot of people that showed up that year. So that was the last time I was here on the basis of being part of the organizing stuff for SEM. I should also mention that as far as this talk is concerned, the folks at Correlated Solutions have been very helpful. You can see the list of folks there that have helped me in the experimental modal analysis studies that we did, and we'll show briefly at the end of the talk. Dr. Knight at the Mechanical Engineering Department at USC has helped. We have a lab there for high rate loading. We've extended some of the stuff that you'll see from XLIII's work at USC, thanks to his help. And finally, again, repeating that Dr. XLIII gave me his entire lab, which is a wonderful facility to do the Tensile-Kolsky bar studies you'll see today. And during that time, I spent 6 months there on sabbatical. Also had access to all the support personnel. Did all the analysis myself, but and the DIC work, but all the basic study, the basic loading of the experiment was done with his staff. So with that background, thanks to all these folks. I'll start out with a brief outline. As I pointed out earlier, there'll be 2 parts to the digital image correlation. There's the fundamental assumptions in it, and then there's the pattern and measurement variability, which are now pretty well known and pretty well established for the technology. Second part will be looking at the Kolsky bar studies in more detail. And finally, the modal analysis application that you'll see is for the relatively standard tuning fork. We'll talk about what we get from the modes from that using DIC. And then we'll finish up with a brief discussion and a summary for the modal analysis work. So what are the fundamentals for the method? The fundamentals are very simple. They deal with the pattern matching, whether you do stereo DIC or whether you do 2D DIC, the fundamental is in the matching of the patterns. So the pattern is where you start. You have to have specific aspects of that pattern to be able to extract visual-based measurements and infer from those the motions of the specimen that the pattern is bonded to or is incorporated within. They're listed here. The deformation motion must be in one-to-one correspondence. There's so many times that I've seen people put on patterns or think they know what's going on, when in reality the pattern is debonded, it's separated, cracks are growing underneath the pattern. It makes it very difficult to extract information when you don't know for sure that there's a one-to-one correspondence. What you see in the image must match what the specimen is doing. That's first. Then you deal with the issues with the pattern, and those are here. First, the pattern must be thin, and it must be bonded throughout the specimen life. Whatever the loading is, you've got to maintain it. The thin is because if you make it too thick, it's going to crack. It's going to behave in manners that are not consistent with what you see in the specimen. The second part is it must be isotropic. Isotropic means, in this case, the pattern must look the same in all directions. You can't have, for example, if you have a line pattern, horizontal line pattern of black and white, it's not going to work well. If it translates horizontally, you don't see anything. The pattern just moves within itself and it's simply unable to predict anything. Transversely to that, you can see something. It's not as accurate, but it would at least give you some information. That's the second part. Isotropic as much as possible. Third, you must have sufficient intensity gradients. You're going to see the equations for it in a minute. But wherever you go, there's got to be relatively steep, strong gradients in intensity, from light to dark, with as much gradient as you can. 230 for an 8-bit camera, 0 to 255. You'd like to see 230 to 40, the range being around 190. That would be ideal. For 10-bit, 12-bit, 16-bit cameras, similarly, you need a large range to ensure you get high quality in the matching. Okay, we'll see the equations that show that. Pattern variability. What I mean by this? What I mean is standard CCD and CMOS cameras, most CCDs are gone today. We have primarily CMOS. These camera sensors are sensitive to the photon noise, the thermal background noise. They will vary in intensity by just sitting there. If you take 1,000 images and you look at a pixel, it's not going to stay 50. It may be 49, 51, 52, 48. It oscillates. That's noise. You're using the cameras to acquire images and you're going to analyze those images, so that noise affects the accuracy of your predictions. The point to be made in that is that that noise is Gaussian. It's been proven many, many times over. The downside of the Gaussian is it's not the same in light and dark. A relatively bright pattern has more noise in it than a relatively dark pattern. So for those that are doing DIC, it's always better to have a relatively darker pattern than it is light. It doesn't look as nice, but the noise levels are lower. Therefore, you're going to get better accuracy as long as you have a sufficient range and intensity to acquire the data. Here's an example, just a brief example. What you see here is a relatively isotropic pattern within that subregion on the left, top left. The photon noise, I should tell you, is about 1 gray level in scientific grade cameras out of 256. So it's about 0.4% noise. That's standard. You can get some that are better, but not much, unless you want to thermally cool them. There are thermally cooled specimens, camera sensors, but they are expensive, and oftentimes the cooling process itself is not necessarily good. There can be vibrations associated with the cooling system that can affect your accuracy. So if you can cool it and you do it in an effective way, you can see at the bottom that the gray level noise goes down. That's the width of that. The width of the variability and intensity decreases. The cooler the camera, the less noise you get for each pixel. The best I've seen in cooled cameras that we've used over the years is plus or minus 0.5 gray levels. We try not to use thermally cooled cameras much because they do cause their own issues. Historically, it's been a problem because of the cooling system itself. Now, as to what is the relationship between the noise in the cameras and the accuracy of the measurements you make? This was demonstrated fairly completely by Dr. Wang in 2009. She developed a general framework to show you how intensity variations propagate into noise in the displacement fields that you measure. She did it in 2 dimensions, which is all you really need for cameras because the camera sensor planes are planar. They have very few curved ones out there. So I'm going to show you what it looks like for a 1-dimensional case. But the bottom line is it's been done in 2 dimensions, and therefore we have a feel for how the equations and how we can predict the error in displacement given the intensity pattern noise that you see. The journal article is at the bottom if you ever want to read it. It is rather dense at times, so if you're going to read it, it may take a little bit. Here's the equation at the bottom. The variability in displacement is directly proportional to, in this case, this is the variance, the mean square of the measurement standard deviation, that is the displacement minus the exact value, is twice the standard deviation squared in the noise in the camera, divided by a very important term. It's a summation of the gradients squared within the subset. So here, if the gradients go to 0, you can see how big your error is. It's infinite. So you can't be trying to predict what happens in an entirely black region. You won't have anything with any accuracy. You got to have appropriate contrast in your image within the subset of the image so that you can extract good information. What most people don't realize is you can get this estimate in your error before you ever run an experiment. If you just think carefully what this means, you can take your images before you ever start. You can estimate, if you can estimate the standard deviation in the intensity of the camera, and you can do that by acquiring a whole series of images, 500 or 600, just sitting there, acquiring those images, and then analyzing them with image correlation. The difference between that and 0 is your standard deviation. So you can square that and you have your variance in the noise in the camera. That's sigma I squared. Then you can go in and if you want, for each subset, calculate the gradients of the intensity, square them and add them up. Before the experiment is even run, you have an estimate for the error that you're going to get in your measurements. Most people don't do this, to be honest with you, because there are some issues that we'll talk about briefly, but you can do it. If you really want to, it's there for you to do. Going back to the isotropy for just a minute and the equation, this again goes back to that gradient. Here is the same pattern looked at different magnifications. In the far left, what you see on that subset is generally a fairly isotropic pattern. If you look carefully, it's not quite, but it's very close. So the errors in all directions would be circular. You wouldn't see much difference anywhere. As you get a little bit higher mag, you start seeing slight differences. The center region now begins to show some directionality to the pattern. Moving further to the right, by the time you get to the far right, now you have some horizontal regions. So the accuracy in the vertical direction is not bad, but horizontally the accuracy becomes much less. So the directionality in the pattern in each subset will give you errors that increase or decrease depending on the level of isotropy in that subset. So be aware of that. When you're working with patterns and you look at them, this is something you should check to be sure you have a quality pattern to try to get the best accuracy. Well, in the background of this is a story I have to tell. It's not pleasant for me personally, but I'll tell it. When we first developed this method back in the 80s, Dr. McNeil and myself and Dr. Chow struggled with one point. No matter what we did, the best we could ever do for the error was plus or minus 0.01 pixels. And for many years, people have repeated that. It's plus or minus 0.01 pixels. You can't get better. Well, I kind of thought that was true until I had a student from Germany show up named Hubert Schreier. He showed up in 96, and in 99 I brought him into my office, and I was saying a lot of four-letter words about not being able to figure out why this was kind of a standard value for error. Is there something we're missing? And I told him, work on this. See if you can figure out what's going on. Well, 6 months later, just before the turn of the year, Dr. Shire walked into my office and dropped a 15-page paper, completely written on my desk. And in it was the answer. So I can tell you that as far as I'm concerned, it is the most important extension or development in image correlation. And it says, he proved that an optimal interpolation function selection is critical. If you pick optimal interpolation function, it will dampen out noise and increase the accuracy of those gradients that you have in your pattern. As a result, as it moves by using optimal interpolation functions, the error is no longer 0.01. You can see here, it is down to 0.0025 pixels. It is 50 times smaller. It was a shock. So we actually went in and did some experiments. We said, wait a minute, is this true? At the same time, Dr. Schreier sent me this graph. It turns out that with these optimal interpolation functions, if you have pure translation of a subset, so it's simply moving very stepwise from 0 to 1 pixels, that there is a very, very slight bias. It's the mean value, even if you average it out, is not 0. That is, there's a slight shift in the value that is a function of how far you move. And it's at 1/4 pixel and 3/4 of a pixel of motion, you get the maximum error. At 0, 0.5, and 1, you get no error. Well, we decided to try this. It's kind of hard to do. We did it in 2006 with a colleague of mine who had a nano translation stage at Maryland, and we saw it. We were able to show that this theory matched with what we saw. And the errors were down around 0.0025 or even smaller for this bias, this very slight change in the mean value. So even if you get rid of all the standard deviation in the noise, there can be a very, very slight bias in the data. Now that's for pure translation. In strain, as the subset stretches, they don't all move the same amount. As a result, if you even get as much as 500 microstrain, 200 microstrain, the bias disappears. It's gone from the subset and we don't see it. But we had to prove that the theory was right. So we went ahead and did the experiment for pure translation to show that what he was seeing theoretically matched with what we saw. So that turns out to be a very important part. Today we use this all the time, and the errors can be extremely small in strain if you have reasonable averaging of the data, especially for quasi-static cases. And you'll see the same thing for some of the modal work. Where are these kind of things important? Somebody said, well, it's just noise, I don't care. You just get rid of it. Well, you can't really get rid of it in some cases. And here's some examples. We've done some stuff with with fine element. We tried to input the boundary conditions with DIC data. The problem with that is, for those of you that know much about the solids part of this, errors on boundaries propagate quite a ways inside, and they're not small. The errors in the stresses near that boundary become very large. So slight errors in displacements on the boundary can propagate to relatively large errors in stresses you're predicting on the inside. So you need to either smooth it or do something with the data to try to improve it. And you got to understand the level of noise you're getting, and that's what these equations tell you. The point-by-point comparison to fine element predictions has been a real stickler. No matter what you do, if you're going to use DIC data and not smooth it or not do something with it, there's going to be noise. So you can't expect to get exactly the same value as fine element, which doesn't have noise, it thinks it's perfect. Okay, well, that's not data. And so you have to expect some differences depending on the level of error that you have in your measurements. And you look for that when you're trying to compare them. If you're in that range, you don't worry about it. The other part is obviously for a lot of the things that people here do, velocities and accelerations. Obviously the noise and displacement is going to propagate dramatically into the velocity acceleration errors, and those propagation equations are well known today. So you can minimize that by fitting and by a variety of methods, but it's still going to be there. And you have to be able to deal with that. The other one that I've been working on more recently is inverse methods. There's a lot of inverse method work going on. Kaushik Bhattacharya at Caltech has been very active recently. in doing this, where you take DIC data, and particularly strain data is predominantly used, but you can also just use straight displacement data and differentiate it to try to predict material properties. So you have some known boundary conditions, you have measured strain fields, for example, and you then predict the material properties that give you a good match. And so that's part of what's going on today. So all of these require you to know something about the types of errors you're getting. A validation for this, has it been done? Yes, it's been done. It's been done a lot of times today. Phil Roy, who gave a talk, workshop earlier, was one of the people that was actively involved in that with me back in the early mid-2000s with Dr. Wang. He continues to do those kinds of work at Sandia. The one we did was a synthetic. We developed a synthetic pattern using the procedures described by Dr. Schreier. We used an average speckle size, 4x4. We used 16-bit images, so we got a nice bright range. Gaussian noise of 2.7%, much higher. We ranged it between 0 and 2.7% Gaussian noise. We translated, we compared it to the theory. And on the right is the comparison. The theory is the line, the simulation data of DIC are the dots. If you look carefully, at about 2.5% it begins to deviate. You may wonder why. That's because there's a second order term that we didn't include. For very large amounts of noise in the camera, you'll have to include that. Unfortunately, or fortunately for us, the noise in most cameras is much smaller than that. It's about 1%. So you're down in the range where the first order terms match well with the experimental or the simulation data and the theory, as well as what we did with Dr. Bruck for the translation studies. So, in summary for this, if you place a pattern on the surface, you can predict the standard deviation and displacements directly simply by using an analysis of the image ahead of time. It does require you to have certain software available to you. You got to develop your own DIC software, or you just got to use one that's available to do that. Most people don't even bother with that. They go the experimental approach. We do that all the time because we do have our own software to do that, of course, but I don't do that. The students prefer just to take a series of experimental measurements. We take 150 images with no motion. We take that camera and with the subset size and subset spacing we select, we simply do correlation and find the standard deviation. And that standard deviation and displacement is what we use for our error assessment. It works very well. So that's a way to get around having to use that equation and analyze the images, but that one is always there if you have the right software, if you just are curious about it. So that's it. That's a little bit of a background on DIC. I'm not going to talk much. I'll show you the errors and all that. You'll see the pattern that we used, although it's a little bit dark because I wanted to keep it dark to get minimum noise in the pattern when we're doing the DIC on the high rate loading experiment. But that's the background for what you're going to see now. This is all Tinsel Kolsky-Bart at Ohio State. If you ever get a chance to see his lab, he's got 3 labs. They're about the size of half of this room. Pretty cool place. Anyway, in this case, we're going to apply the tensile loading to it in Hopkins and Barr, which is high rate loading. It's wave propagation loading. We're going to impact one end. We're going to pull one end of the Kolsky bar. It's going to propagate a wave down the first bar into the specimen and through it into the second bar. As it moves into the specimen is where I'm interested. I want to know what's going on with various stages, and can I predict the inertial stresses? And when I say predict, in reality I mean measure. Physically measure the inertial stresses. So let's see what this is going to look like. And to do that, of course, we're going to have the one-dimensional wave equation. Kolsky didn't develop that. It was done by others, but the Kolsky bar system, or the split Hopkinson bar, is the one we use today. This is going to be brief. Most of you have seen this in one form or another. This is the 1D version, okay? That's all we use for the predominant use in analyzing the data from the Hopkinson bar. You can do a series of simulation, a series of calculations in this to go down to one equation. By moving through, solving it, doing different modifications to the equations, you end up with the equation right here. This equation is the one I want to talk about. It's the equation that you see on the far right. The far right term, the integral, is what we call the inertial stress term. It is the integral of the density times the acceleration over the length from 0 to the point you're interested in for any time t0. This inertial stress term can be directly calculated. You can see already. If I know the acceleration at time t0 at every x along the bar, then I can simply integrate up to that x and calculate the inertial stress at that instant, at that point. A very simple set of equations. Frankly, it was a bit of a surprise to me once I got into it that this was more easily reduced than I thought, but that's the key to the whole analysis, is that equation. So by using that equation as a starting point, the question was, can I calculate those accelerations effectively? And if I can, then I can do the integral using a Simpson rule, if you will, and simply extract the inertial stress at any time. So that's what we're going to talk about today, the process of doing that. Not much to say here. This is, for those that don't know much about the Hopkins bar, I'm just going to briefly explain what we have here. In this case, the far right end is going to be pulled instantaneously, sending a stress wave down the bar from the right to the left. The specimen is here. It propagates through it. It passes through to the back end where you have some sort of damper that drops the stress wave out. So in this instant, I'm looking only here. This is where the specimen is. The HPVX cameras are here and here. These are 2D. I won't talk about the data from this one. We used it for validation check. That's all that was used for. We used the data from the camera below with all these various devices to synchronize the image acquisition with the wave propagation. That's all that was for. So we had to know something about where the wave was so we could start taking images and not miss the wave propagation into the specimen. Here's the specimen. You can see the wave is coming from the right. It's propagating in toward the left, so X is going to the left. Y is vertical. Don't much care about Y at this point. And we're going to determine the initial stress field. And the initial stress field will be when I say initial, at any time t0. We'll be able to get the inertial stress all the way across at any x. I'll show you how this works in our case to show you how DIC can be used for this. In this case, as you see at the bottom, I acquired, in this case, 140 images as the wave was propagating across. During that time, the subsets that we used are shown at the bottom. They are the entire region across the specimen. The advantage of that is that I have an isotropic pattern. There's a lot of subsets, but they can be wide because I'm only doing the 1D part. Don't much care about what goes on vertically, not interested in resolving any gradients in that direction. So I simply use large subsets that extend along the length. And there, in this case, it's shown, I had maybe 25 or 30 along the length. Took data at each instant to get the displacements. Use those displacements at each instant, at each position along the length to extract the displacement field. And then I analyzed that first, be sure what I saw made sense. And then I began to analyze that to get the velocities and accelerations. So that's the background. Once I get the accelerations, I use the integral at the bottom to get the inertial stress term. Here's the specimen up close. For those that have not used it again, Dr. Galat and I found out real quick that you needed to use the right kind of attachment. The specimen, which is shown at the bottom, was bonded into the grips. Those two grips that you're seeing were then bonded into the Hopkinson bar setup, and that was critical. Our early experiments did not work, Most of you will guess why. It pulled out of the grips. And the grips were then modified and replaced by using these. These are non-reusable. You throw them away. Okay? So you do experiment, you move on with this. So that's what this experiment shows you, that you have to set up the experiment correctly for your example so that you can get data that makes sense. We had to do this. We did several of these before we found the right way to do it. Here's the data for the Shimazu HPVX camera that we used. Displacements were 5,000ths of a pixel. That's the standard deviation. It's pretty good. These are single shots. Remember, I can't average images here. There's no averaging of images. There's no reduction in this noise level. That's what you get. That's your standard deviation. And that's only, in this case, that's pretty small. It's turned 80 nanometers. So the error, the variability in the specimen displacements I'm going to measure is 0.28 microns for each shot. Subset size is shown on the right. We used 17 by 17 pixels squared. And for the strain, we used a 21 by 21 array because I moved the subsets 1 pixel at a time. So I used 21 data points to get the strain field. And we used the variability that I got from 140 undeformed images. I used the experimental approach to calculate the variability. Here was the initial set of data that I got. The important part is to look for where the wave showed up. You see it 3.5 millimeters down, which is 3.5 millimeters down the bar from the right to the left. The whole length is 15, remember, so it's about a fifth of the way down. You begin to see the wave showing up. The displacement increases, but it only increases after the wave finally shows up at this location. And as you move to the 7.5 or 7 millimeter, a little bit further down and so forth. So we're picking up the wave. The displacements, as the wave is propagating down, I'm seeing them. I'm picking up, I'm measuring what should be there. So I was confident at that point that I could start using the data to extract the accelerations and other data of interest to me. So it took us a while to get this. Again, remember we had to replace all the grips and all that work, but once we got there, we started getting good data. It took me a while to analyze it, but this is what we got. Out of that, I got the velocities. I just used a straight central difference. Did not smooth this data. This is just straight up central difference shown here. And you see there's a good bit of noise in the velocity field, but it's not bad. You see the increase in velocity. This is at x equals 0 millimeters, the left edge, as a function of time. The velocity is increasing as the wave is propagating in. And at 15 millimeters, the velocity it's kind of flat initially, and then it picks up as the wave gets there and begins to increase, but at a much lower level, and then drops off to steady state. Notice both of them show steady state. The steady state, in this case, is where the acceleration has gone to 0, and that's where you always acquire data with the Hopkinson bar. I'm acquiring data down in the left side, up to 30, in this case 30 to 40 milliseconds, or microseconds rather. That's where I'm interested, where the acceleration is increasing, because that's where the inertial stress may be important. Here's the acceleration field. You can see how I did it. It's a very blunt force method, a 13-point moving average on the velocity to get the velocity, and a 19-point moving average on the velocity to get the accelerations. So it's a very smoothed version of what's there. We tried a variety of methods. This is the smoothest and easiest one I could find to do at the time. Did fit a quadratic function from 0 to 4.5 microseconds because I couldn't get data down there because of the large smoothing window. But it looks good, and we can see the accelerations increasing and then decreasing as the wave propagated through. And most importantly, this is the inertial stress field at the far left end of the bar. The maximum inertial stress was 7 megapascals at that location. All this was done with DIC data. We have done some simulations independent of that. Results are in general agreement. They're a bit off because of all the boundary condition issues and such, but in general, the results match up fairly well with what I saw. In closing, these are the last two curves. We did get the strain rate in the GAR, and we also compared to a strain gauge. The strain gauge comparison is on the left. The strain gauge is a lot more noisy than the DIC data, but that's another story. And the strain rate data from DIC is shown there. And the strain rate, when it reached steady state, was around 350 per second, which is reasonable for this kind of a test. That's it. Brief summary of that. Move off to the modal stuff that all you guys are interested in. So, in summary, it works. You can use it for high rate loading if you're interested. The methodology is very effective for these scales. You simply have to have the ability to go in and analyze the data post-experiment and then determine the stresses and deformations using appropriate filters. And the local strains in this case, the noise and strain that I got from my data on the order of plus or minus 200 microstrain. Did not spend a lot of time, because it's a dynamic experiment, I can't do image averaging to reduce the noise levels. That's just what I got in this case. Okay, so move to the last part of the talk, and that's the modal analysis application, a relatively simple one, just to show you what's feasible today, what's been done with stereo DIC in the modal studies that we've done. And in this case, it's a tuning fork example. In this case, you noticed earlier that the noise levels for the Shimazu HPBX were about 280 nanometers. A lot of the vibration modes have much smaller amplitudes than that. So the question is, if we use a lot of images of the vibrating system, can we extract noise levels that are much lower? And the answer is yes. You're going to see that in the data. So we can pick up relatively small amplitude modes, the operational deflection shapes, using the averaging approach to extract higher levels, lower levels of noise and higher level of accuracy in the displacements. What we're going to get out of this are the operating deflection shapes in the low and high frequency range. The fast Fourier transform, we perform that both on the modal hammer and on the accelerations. Didn't show that here, but we also did on the accelerometer that we attached. We also get the frequency response functions now. It's fairly new, using the modal hammer results. Visualize the mode shapes, and then we look at a brief summary of the noise that we get in the measurements. Again, the noise can be directly determined using various equations. Particularly if you use averaging, then you can do it again consistent with the theory I showed earlier. So for this case, tuning fork is shown up here. In this case, X is to the right, Y is vertical, Z is coming out at you. For this, the software we're going to use is VIC-3D, the three-dimensional software we have available. The cameras are here. We're using them at 1 megapixel, 6,400 frames per second. Okay, that's what you get. Now we're going to change that slightly for our application, but that's standard for these cameras. We use zoom lenses. We can either look at a local range or further back for a broader range. And as you see on the right, we do have a halogen lamp. That lamp was only used for calibration. There's a disadvantage to using halogen lamps. Most of you know, it heats things up. I don't need to have things heated up, particularly the tuning forks. So we turned it off after we did calibration. And if you can't see them, but on the far left and right of these are diode lights, low heat diode lights that we use to illuminate the tuning fork. It's a fairly straightforward, simple system in this case to use. The calibration process, of course, you always perform ahead of time for the stereo system in preparation for the test. What is the non-DIC software or hardware we used? We did use an impulse hammer from PCB, Piezoelectronics. Its sensitivity is shown here. We also use an accelerometer attached near the root of the tuning fork, and it's shown there with the sensitivity. We use signal conditioner to synchronize all this. We want to synchronize the image capture with the tuning fork information, the forces from that, as well as the accelerometer. So that was done. The one we used in this case was called a medical grade tuning fork. 174 hertz was one of the lower frequencies that this one has. I'm not sure what healing frequency is. Maybe I may need to use that. I'm not sure. Anyway, you can see the hammer on the far right, accelerometer there. Now, back to the DIC part. In this particular application, we doubled the frame rate to 12,800, reduced the resolution, 1024 by 512. We don't need much vertical. We're interested in what's going on horizontal, so it doesn't hurt as much. Use 2,000 image pairs. We could use a lot more. We just use 2,000 for this example. The subset size we used for all the image correlation was 19 by 19. Spacing was 4 pixels. The FFT spatial smoothing filter was set at 4, and the FFT sampling step size was 4. We used both hand and hamming window functions with also no windowing function. We'll show the results from all three so you can get a feel for the differences. Most of you know what that's going to look like already, but we'll show that just for completeness. Here's the main part of this. I guess this is the primary reason for me being up here is to go through this. Obviously, if you want to stay twice the Nyquist frequency, if you're wanting to get 5,000 kilohertz in your mode shapes, you need to at least sample at 10,000. In our case, we recommend that you operate at 3 times that. We found that to be the ideal range. So you need to run at 15,000 kilohertz, 15,000 hertz on your camera or frame rate to extract mode shapes up to 5,000 reliably. You'll see here that we did that. We're doing 12,800, so we could extract up to 6,400 reliably. And if you do it 3 times that, we're down around 4,000. We can pick up with great confidence. We'll see we got slightly better than that in this case. But you pick your frame rate to be sure you pick up the mode frequency range that you want. You then, as I said earlier, you calibrate your stereo system first. That's the first thing. You set it up and calibrate it, and then it's done. You're ready to go. You set up everything so that you've got the modal hammer force input and the accelerometer input, and you put those through the DIC system, and you're going to excite this, in this case, the tuning fork or your structure with a modal hammer in this case. That triggers the DIC system because they're all synchronized, and you download at least 10,000. We downloaded 1,000. We downloaded 2,000 for this case. We've done a lot more than that, but 2,000 is more than adequate for this case. And we're looking for the higher frequency operating deflection shapes just to see what we can get there. Software package is all here. All this is now more or less automated. Once you get into it, you can analyze the images directly. You simply import them and they analyze them. It exports, import the analog data from the DAC, that is the accelerometer, and the modal hammer input all comes in together. It does FFTs on everything and does the windowing functions if you want them. Both hand and hamming are available. And from that, you visualize the data once you're done. You can output it, look at the frequency response functions, which are now available also, and you export it in CVS or whatever universal file format you want for use outside. So as far as the windowing is concerned, you guys know the windowing function has its own issues. You got to be sure you have enough understanding of what frequencies you're looking for, that you don't dampen out something that you're actually seriously trying to locate. In our case, it's very important because we have displacements. We're measuring displacements, not accelerations. So if one end of the hammer moves slightly, then you can see that this end over here starts at 0, this end moves, you have a difference in displacement. Cause 0 to something over here, rigid body translation. The filters are very important to smooth that out and flatten that to be 0 on both ends. We've learned quickly that that's something you need to use in this case, unless you're certain that both ends are stable at 0 and the rigid body end or whatever component you think is stable is really that way. It's not moving. So for displacements, the windowing functions become important. It does reduce the amplitude, of course, as you guys know. Here's what they look like. The frequency response of the tuning fork with no window on the top left, with the Hamming window at the bottom left, the Hamming window at the top, and they're combined down below. And you can see that the windowing functions do drop the amplitudes. They sharpen the peaks quite a bit, but they do drop the amplitude considerably, almost a factor of 10 for the hand window. But from these, we can extract peaks. And from those, we can then find the operating reflection shapes associated with those. And what we found in this case, we found several frequencies ranging from 60 to almost 5,800. We found the 174 also. The important part for me, I wanted to show this, was the noise floor was 15 nanometers. That is 20 times better because of the averaging caused by the ability to use these sinusoidal vibrations that you're seeing to extract improved accuracy in each displacement. And that's the important part. So it's 9 times bigger than the, in this case, the lowest amplitude peak we're going to see is 134 nanometers, and this peak, this floor is 9 times lower. So you can pick up very small amplitude vibrations with DIC if you know what you're doing in this case. These are just showing examples. This is the 60 hertz that pops up. It's very standard. You guys all know what that looks like. The 174 was the one I need for my back, I think. I'm not sure that's going to help my back. I don't think so. Okay, there's the high. I want to show this one. There's a whole bunch. I'm just showing all those. This one's interesting because this is that one that is very small amplitude, 134. You can see the noise. You can pick it up, but the noise is clear. There's noise in there because of just the limitations. In this case, the 15 nanometer noise shows up, and here's just a sum of all of them to finish out on these. Finally, the modal frequency response functions are now available. You can use those. We hadn't had those for a while. Now they're available, and you can extract those, and these are the ones that are available. The compliance, motility, accelerants, and then their inverses. Stiffness, impedance, and dynamic mass. Okay, that's a summary. Here, we can use those for a variety of things now. We've shown we can, the basics for it are in computer vision. To make it work as best possible, you're going to need to use optimal interpolation functions. They're available. You can develop them yourself if you wish, or you can use what's existing today to do that. To get for modal analysis, the operating reflection shapes are one of the things we can generate. We can get accuracies that are very high for modal because of the averaging process. You also use it for a wide range of other things, including dynamic impact studies, even wave propagation. And that's it. Thank you.